So we're here today really to just show you the type of work that we've been doing on the Alpine Fault in the last few years, and we hope to give you a bit of an insight into how we find out new data about the fault and about the earthquakes it produces. It's planning for the next Alpine Fault earthquake that's the real challenge, and figuring out what to do about these hazard updates when we do get new numbers. So as scientists, we really just want to help that process by giving you new information when we can. So the Alpine Fault's been a huge deal for earth scientists ever since Harold Wellman discovered this beautiful straight line in the landscape and figured out that the rock types on each side of the fault had been moved along that fault over 400 or so kilometres. And back then he didn't even know about plate tectonics. I guess now we know that this is the boundary between the Australian and the Pacific plate, and the Alpine Fault is taking up a lot of the movement that's happening between those two tectonic plates. Now also we have amazing ways of imaging this fault, so we can look down on it with satellite images, we can drill into it, we can map it offshore. This is some really detailed offshore mapping from NIWA to show that the fault does continue offshore near Fiordland. So there's a lot of research going on around this fault. Today we're only talking about earthquake geology, and earthquake geology is really about finding faults in the landscape. So here's the Alpine Fault as it runs offshore near Milford Sound, and we use this landscape information to map our active faults. So here's an active fault map for New Zealand showing the faults that we know about for the country. And once we've found faults, we try to characterise them with how active they are, how many earthquakes they have in certain lengths of time, and what kind of earthquakes. So each of us will give you a little short story on what we've been working on. That will take about an hour. We realise it's probably your lunch break, so feel free to leave whenever you need to. But we'll also stay around afterwards for questions. So I want to talk about two projects we've been doing on this very southern southwestland section of the fault. We have an unparalleled insight into the fault's behaviour at this very special site called Hikuri Creek, which is on the eastern shores of Lake Makero. It's at the end of the Hollyford Track, for any of you who have done that. And we've just recently been working at John O'Groats River to improve this data set. So this is right down near the mouth of Milford Sound. So firstly, what's a long earthquake record and why is it useful? Well, from a geologist's perspective, it's just a long period of time that captures enough earthquakes that we can really understand how this fault is moving. And we want to do that in order to forecast into the future and figure out what's coming next. So if we forecasted into the future just using a short period of time with a few earthquakes, we might follow the pattern like this. Whereas if we forecast into the future using this long earthquake record, we might follow the pattern like this. And from the perspective of now, this represents two very different hazard scenarios. So from the short earthquake record, we'd be saying we're about to have an earthquake. From the long earthquake record, we'd be saying, well, we might be up for a big gap with no earthquakes. So we really want to find out more reliable estimates for these earthquake recurrence patterns and their frequency and time. And we know from examples around the world that faults behave in different ways, and some of them really do rupture relatively regularly in time with earthquakes equally spaced. Others rupture completely randomly in time, and there's even some patterns of clustering where you have a whole group of earthquakes happening and then big gaps. So in Southwestland, here's the timeline with us here in 2015. Before this long earthquake record at Hikuri Creek, we did have a record for the last 1,000 years of about 3 or 4 earthquakes, but they were quite hard to reconcile from different sources. So the blue curves here are direct evidence of rupture across the fault line at Haast, but quite poorly dated. So for all we knew, the earthquake could have occurred any time within that blue curve. And we also have a record of beaches and dunes from Haast, which were very well dated by tree rings. So the timing was concise, but not direct evidence of fault rupture. And if we would try to forecast into the future from this record, how do we know what's going to happen next? And if we're going to take an average recurrence interval, we've only got 2 or 3 gaps with which to average out. So it's not going to give us a very reliable estimate. We really wanted a longer record. But we can't just go out and get a long record wherever and whenever we want. So what are we looking for, really? These are the special sites, and you might look at them and go, we chose them for their scenic value or their wilderness status, you know, a couple of weeks camping in a tent, yeah, looks good. But no, actually, geologists have been working here for a long time. So Harold Wellman back in the 1940s was working at this site, and some big names like Calvin Berryman and Rupert Sutherland and Richard Norris have all worked at these sites in the past and thought about the potential for an earthquake record. And the only thing that's changed, and the reason why we get to do the awesome job, is that radiocarbon dating techniques have really improved, and we can now date tiny bits of plant material and get really accurate estimates of ages of earthquakes. And so that's why we've been able to develop a long earthquake record. If we look at the landscape here, you can see the fault line is actually uplifting uplifting the downstream side on some of these streams. So a little stream's running down the valley, hits the fault scarp and can't get through, so it moves along the fault scarp until it can cut a channel. And same at Hikuri Creek, it's coming out of this gully, hits the fault scarp that's running through here and has trouble flowing out to the lake. That's the key to how these sites are recording earthquakes. If we look at a block model, you see that between earthquakes the stream can flow over the scarp happily. But in an earthquake at these sites, this block will move with respect to this block 7.5 metres horizontally and 1 metre vertically. So that will act immediately as a dam to the stream. The stream will flood this valley and bring down silt and sands from the catchment to flood over the valley floor. And if we take that same model and cross-section to see what's happening at the ground surface, you see beforehand in this area we're just in a wetland swamp accumulating soil. The fault moves and that scarp gets raised again. You get the flooding, and the flooding brings down silt from the catchment, so you end up burying your soil. And this cycle repeats again and again because each earthquake makes more space for these sediments to accumulate. So what it looks like in the field, if we look at the banks of the Hikuri River here, you see alternating soil, peaty units with silt, the light grey units. And at the boundary between these two units is an earthquake. We did do quite a lot of detective work to prove that these were earthquakes and not climate change. We looked at fossil algae, microfossils, to look at the past environments of these sediments. And then we sampled for radiocarbon so we could get these really accurate ages. We did about 100 radiocarbon samples because in the end we found evidence here for 22 earthquakes over 8,000 years. The main problem with this site was that we were missing the most recent 1,000 years, so that's why we went to the John O'Groats site, which looks like a modern analogue for Hikuri Creek with this drainage being blocked by a fault scarp. There were no outcrops here in the riverbank, so we cored the valley floor and found very similar sediments to those that we'd found at Hikuri Creek, with soils overlain by silts and these sharp boundaries representing an earthquake. So again, we radiocarbon dated them, and here we got evidence for 7 earthquakes occurring over 2,000 years, so that perfectly filled the gap that we were missing from Hikuri Creek. So if we just remind ourselves of what we knew before, here's the timeline with us here in 2015, and we had those earthquake records from near Haast about what might have happened on this section of the fault. Here is what we know now, with the black curves representing ages of earthquakes from Hikuri Creek and the green curves earthquakes from John O'Groats wetland. So I just want to do that again. This is what we knew before. This is what we know now. So 26 earthquakes occurring over 8,000 years. And this is quite rare worldwide just because of the number of earthquakes we now have evidence for and the length of time over which they're recorded. The main message that you can get immediately from this is these earthquakes have been happening reasonably regularly in time for 8,000 years. There's no way they're going to stop now just because we're living here. Okay, the next event is inevitable. What you can also see is that we have enough events now to get a reasonably accurate picture of how this fault ruptures and how often it ruptures. So in terms of a natural system, this is actually recurring amazingly regularly. There are some big gaps in time between earthquakes and some smaller gaps in time between earthquakes, but if we compare it with faults worldwide, here's our Alpine Fault record at the top with regularly recurring earthquakes. On the San Andreas Fault in North America, you can see that the frequency is much greater, so there's about twice as many earthquakes in the same time, and it's reasonably regular too. But you compare with faults, for example, in the Dead Sea Rift, this is what random occurrence looks like, and here's some more clustered behaviour with little groups of earthquakes and then big periods with none. So this really tells us, yes, the Alpine Fault on international scale is a regularly rupturing fault, and that's what will inform our hazard calculations for figuring out when the next event's going to happen. If we zoom in a little bit more closely to look at those gaps between earthquakes, from the Hikuri Creek record we got the longest interval being about 500 years, the shortest interval 140 years, with the mean recurrence 330. Now with the additional earthquakes we found at John O'Groats River, that recurrence interval was updated to more like every 300 years, and the last major earthquake on this section was 298 years ago. So that shows us we're heading right into that period where we're expecting an earthquake. And there have been 10 intervals shorter than that in this record. When you do the statistics on this original Hikuri Creek recurrence interval, you get a 30% chance of that section rupturing in the next 50 years, but we haven't done the new calcs for this updated recurrence interval yet, and Jamie will be also showing you some numbers for the central section. So this probability is likely to change in the coming months, but it still stands as it is at the moment. And what I mainly want you to take home from this part of the talks is that we now have evidence for 26 large earthquakes recurring regularly in time over the last 8,000 years for that southern section of the Alpine Fault. That gives us much greater confidence in our hazard estimates.
G'day, so I'm Jamie. Ursula's just given you a really excellent talk about one dimension of the seismic or earthquake hazard problem, and that's the frequency or recurrence of earthquakes at a single point on the fault. Another really important component is how much of the fault ruptures during these earthquakes, and what sort of magnitude of earthquake are we going to expect the next time the Alpine Fault ruptures. And indeed, this is actually a really hard thing to get at, because in order to reconstruct information about how much of the Alpine Fault breaks during these big earthquakes, we need to compare evidence for the timing of earthquakes at multiple sites all along the 400-kilometre strike of the onshore Alpine Fault. Now, a lot of research has gone into this over the last 20 years, and we now have pretty good constraint on when the last earthquake occurred in 1717 and how much of the fault broke during that earthquake. And we know that it ruptured from at least as far south as Milford Sound all the way north to just past the Taramacau River, which is about 380 kilometres of the fault, in a magnitude 8.1 earthquake. However, we have relatively patchy evidence for how much of the fault broke during preceding earthquakes. And this is a problem in the same way that Ursula was talking about, because in order to predict how much of the fault will break during the next event, we really want to have many events in the past that we have this information for. We took a slightly different approach to the problem to conventional paleoseismic approaches. So in the approach that Ursula talked about, she was looking at evidence for actual throw or movement on the fault. In this instance, we're actually looking at measures of shaking. And lakes actually act as nature's seismometers, and these are the settings that we've been working in. So you'll be familiar with GeoNet and the seismologists that work for them, and the network of seismometers across the country that they use to predict where when and how much shaking you get during earthquakes. Well, lakes have been doing this for over thousands of years, and they do it because sediment is continually accumulating in the bottom of these lakes, and when you shake them, you produce specific types of deposit that we can identify as the product of that shaking. And what's useful about these sedimentary settings in the context of the Alpine Fault is that we can date those shaking events precisely, and they occur all along this 250 kilometre central section of the fault, which is most relevant for those living on the west coast and indeed on the eastern side of the Alps. And so today I'll be talking about results from Lake Ellery, which is just south of Haast, all the way north to Lake Canary, which is inland from Hokitika. So, how do these lake basins actually record seismic shaking? Well, they do it in a number of ways. So these lakes are located within about 3 kilometres of the surface trace of the Alpine Fault, and when you break that fault you generate really high intensity shaking. And this causes sediments that have accumulated on the margins of the basin to fail in underwater or subaqueous landslides, which sets off a trigger of sets off a sequence of events resulting in turbidity currents, a local seiche or tsunami in the lake basin, and deposition in the middle of the lake of a specific type of deposit which we call a turbidite. And when we see this specific type of turbidite, we know that the lake has been subjected to seismic shaking. There are some other clues. High intensity shaking in mountainous environments, particularly adjacent to the fault break, causes significant amounts of landsliding, and indeed Tom will talk to you a lot more about that in a subsequent talk. And this is an example from the magnitude 7.9 Wenchuan earthquake in China, and you can just see the magnitude of landsliding in the range front immediately after that event. Now these landslides produce a lot of sediment which is then fluxed through our river systems and deposited in depot centres, lakes of which are one of these depot centres. And as we can see here, immediately following that seismic shaking event, we have a dramatic increase in erosion. So that's the products of this landsliding moving through the system and being deposited in the lakes. And that persists for, on average, for decades after fault rupture. We then go back to what we might call normal conditions. So if you look at the range front of the Southern Alps today, these are the conditions that you might expect, and we can kind of have a look at before and after the Wenchuan earthquake again. So these are the conditions that you would have in the Southern Alps today, and this is what you might expect immediately after the earthquake. And again, we can see in here a dramatic decrease in erosion later in the seismic cycle, just before the next Alpine Fault earthquake occurs. So we have evidence for seismic shaking or repeated seismic shaking recorded in these lakes. In order to turn that into useful information about the frequency of Alpine Fault ruptures and also how much of the fault breaks during earthquakes, we need to say something about the intensity of shaking that's causing these deposits to form. And based on the responses that we reconstruct from those deposits, we infer about intensity 9 shaking. And that's exactly the intensity that you'd expect to occur along the length of the ruptured fault during an earthquake. So we have evidence for high intensity shaking, but as I pointed out at the start of the talk, in order to say something about the rupture length of Alpine Fault earthquakes, we need to correlate between sites. And as Ursula mentioned in her talk, recent advances in radiocarbon dating, one of the most important approaches for dating past earthquakes, means that we've gone from generating a date from a piece of wood or organic material of about that size to being able to date these individual leaves. And what that sort of transfers to in terms of an increase in our confidence in our age estimates is documented here. So we've got age on the x-axis, probability on the y, and here's a conventional on-fault paleoseismic age. So the earthquake could have occurred anywhere under this curve, and this is the type of age estimate we're generating from the lakes. And you can see that there's a much lower range of possibilities. So we've got evidence for high intensity shaking, and we can correlate reasonably well along strike because we can date these events precisely. Does our proxy actually, or approach actually work? Well, because we've got really good constraint for how much of the fault ruptured during the last Alpine Fault earthquake, we can model the shaking intensities that would have occurred during that event, And here's the isoseismal of MM9 shaking here in orange, and here's the MM9 shaking that we've reconstructed from the lakes during that 1717 earthquake. And you can see that they agree relatively well, which places confidence in the proxy or approach we've developed. So that's how we go about it. Now let's actually get down to some useful information about the frequency and magnitude of earthquakes in the central section. And I'm going to talk to this with reference to the space for time diagram that we have here. So we've got time over the last 3,500 years on the y-axis, and space here on the x-axis, and here are the lake sites again that we're talking about. And here are the probabilities for the timing of events through the last 13 earthquakes on the Alpine Fault from these sites. And we can determine that they are in fact the same earthquakes using statistics to correlate between sites. And what we find is that during the last 13 earthquakes, the majority of the central 250 kilometres of the central section ruptured during these events, and that equates to a magnitude 7.8 or greater earthquake. The recurrence interval of these events is about 260 years. The maximum interval between events is about 337. The minimum 220. We'll just refer that back to the elapsed time since the last earthquake, which is 298 years, and the fact that 75% of recurrence intervals over this 13 event earthquake record were actually shorter than the current elapsed time. And that's just more evidence suggesting that this is an inevitable event that is likely to occur in the relatively near future. So the take-home messages: our understanding of the Alpine Fault earthquake history are continually evolving as our data quantity and quality increase. And 15 years of effort went into this map of the rupture extent for the last 3 earthquakes, and we now have a much longer record of the rupture extent, which once again places increased confidence in our hazard estimates. I want to take a quick diversion from simple magnitude and frequency of rupture on the Alpine Fault and talk about some of the secondary effects and the possible implications of what's known as the post-seismic sedimentary hazard cascade. So usually when we think about seismic hazard, we're concerned with the seismic shaking produced by the main shock and also the aftershock sequence, which might persist for a few years after the main event. However, in mountainous environments, seismic shaking triggers this sedimentary hazard cascade, and it's initiated by the co- and post-seismic landsliding. So here's the Wenchuan earthquake again, significant landsliding. Tom will talk about this in some detail. These landslides produce abundant sediment, which is moved through catchments and results in aggradation of fans and floodplains. Another example from Wenchuan, you can see here, fan aggradation is actually completely covered a dwelling which was on the apex of the fan. And we know that this process of increased aggradation and sediment flux persists for years to decades after these events. And just to give you an idea of the magnitude, we'll go to the 1999 7.3 Chi earthquake. And here's a dam before the earthquake. And then about 5 years after the earthquake, we've had 10 million cubic metres of sediment flux through the system and completely fill the dam. So we're talking about significant volumes of sediment coming out of the Alps after these events. So I've provided some analogy to events we've been able to observe after other earthquakes around the world, and what is the relevance of that for the Alpine Fault? Well, we have very limited but a few cues that this is important in the event of the next Alpine Fault earthquake, and that comes again from these lake records among other sources. And we can see that we get dramatic increase in fine sediment flux to these basins after Alpine Fault ruptures, which represents a 300% to 400% increase in the amount of fine sediment that's coming out of these catchments. And based on our dating, this persists for years to decades. And the mean of our probability for the duration of this response is about 50 years. However, we've got a real problem, because a lot of the hazards aren't derived from the fine sediment. It's the coarse material that results in aggradation of those fans and floodplains, and we understand very little about the rates and magnitude of that, And it really is an area that we need to focus on and produce some useful data so that you guys having to plan for the next response actually have something to work with.
Yeah, thanks very much. So I'm an earthquake geologist from GNS Science, and one of the things that I do is I study the paleoseismicity of faults. And you've heard from Ursula about a near-fault study, and you've heard from Jamie about an off-fault study. Well, what I'm going to be talking about is on-fault geological studies, because the fault lines themselves have a special geology all of their own. So you'll see today some examples of some historical earthquakes and how they produce surface rupture and surface movement. And you'll see some examples of paleoseismicity, which is where we excavate into faults and look at the past record for the faulting right on the fault line itself. So just to back right up, we know now that large earthquakes occur on faults in the Earth's crust. And these large earthquakes occur following a build-up period of stress across each fault, which we call the seismic cycle, followed by relief of the stress across the fault in a large earthquake. And you've experienced that here, so I don't need to tell you that. But Ursula showed an active fault map of New Zealand, and this is just another example of what we can do with the active fault database, which is divide up all of the active faults in New Zealand into those that have ruptured, or those that rupture every 2,000 years or less, shown in red, and those that are greater than 2,000. And apologies, this is an old map, so it doesn't show the Greendale fault. So basically in the core of the plate boundary between the Australian and Pacific plates, you have the Alpine Fault, a number of faults in the Marlborough Fault Zone through here, the Wellington and Wairarapa faults, heading on into Hawke's Bay and up to the Bay of Plenty, and also a myriad of active normal faults through the Taupo volcanic region. And as an earthquake geologist, I'm also interested in the geomorphology of faults and the sedimentary record they leave behind and the faulting associated with that. So here are some examples of some beautiful faults in New Zealand. The Hope Fault near Hanmer Springs. You can see an excavator here, or about to do the business. A fault trench on the Oharu Fault near Wellington. The Wellington Fault down by Cook Strait, where you see an old ridge line which has been severed and moved along the fault. And here's an example of a scarp of the Alpine Fault, and in fact faulting here. So all four of these things have something in common. There's a geomorphology associated with the fault that we can both map as a line and that we can excavate into and see the evidence of faulting and hopefully date the evidence for past earthquakes. And I wanted to put this into some sort of perspective in terms of the slip that happens in earthquakes. And these two coloured diagrams on the diagonals are looking right at a fault plane surface, and just in the last few years since we've had advanced geodetic or GPS surveying and seismology, we've been able to look at faults and say how much slip is actually going on the fault surface during a large earthquake. So here's two examples, the 2011 Christchurch earthquake and a 2010 Haiti earthquake. In this case, here's the focus of the earthquake on the fault plane, down underneath us about 7 k's down. And these colours represent amounts of slip on that fault surface. So there's a peak of slip under the ground about 5 kilometres down, where there's about 2.5 metres of slip. That slip reduces, shown by these coloured contours, to the point that by the time you get to the surface of the Earth where we all live, there's actually very little to no earthquake slip at the ground surface. In contrast, in the Haiti earthquake, which was a bigger earthquake, the focus is here. These red contours in this case are about 4 metres of slip on the fault plane, and up at the ground surface you're seeing about 1.5 to 2 metres over a length of 20 kilometres, just like you saw in the Greendale Fault earthquake of 2010, or in other earthquakes like this one in Izmit, in Turkey. And so this is the sort of thing as geologists we go out and map following earthquakes. So here in Izmit in 1999, here's the mole track of that magnitude 7.4 earthquake, and there's 4 metres of horizontal movement associated with that mole track. Similarly, for the Greendale Fault in 2010, here's this beautiful surface rupture, and you see, when we can see features that cross it, that there's about 3 metres of horizontal movement across the fault zone. And another couple of examples from the Chi-Chi earthquake in 1999, Whereas normally we know if we build an athletic track, we don't build a hill or a steeplechase in the athletic track. So there was a hidden or buried fault underneath the athletic track, and the fault ruptured and actually rode up the whole track. Similarly, from the same earthquake, I imagine here there was a pre-existing fault scarp that these people decided to build their buildings on top of to have a slightly better view. And when the fault re-ruptured, of course, that's a bad place to have buildings. Moving now more sort of to West Coast specific stuff. About 5 years ago, we got some funding to fly LiDAR along some of the most heavily vegetated faults in New Zealand to see if we could see the faults beneath the trees in the landscape. And LiDAR is a really good technique for that. It's an aerial technique where you fly a plane and you beam energy down to the ground surface. And that technique allows you to, that energy is beamed down and it bounces off the trees, it bounces off tree trunks, it bounces off shrubs, and it bounces off the ground and comes back to the planes. What they're able to do back in the office is subtract out all of the returns that come from all of those other things, and they're able to make an elevation model which is just of the ground surface underneath all of the vegetation. So here you see what we did on the west coast. There's a 1.5 kilometre wide LiDAR swath flown along the Alpine Fault here between about Franz Josef and Whataroa. And this example here comes from Gaunt Creek, where this is what the bush looks like if you ever walked around in the west coast bush. But when you subtract the trees and have an elevation model of the ground, we start to see some quite interesting things which are surprising to us. In this area, there are some north striking geomorphic features that look like fault scarps. This is our old interpretation of where the fault was. And we're very curious about these features. They're very extraordinary. So while the DFDP project was going ahead, here's the interpretation of those faults on a map, quite north striking. While the DFDP1, the deep drilling phase 1 was going on, we actually had a digger up here and we cleaned back the very end of this fault trace. Here it is shown in exposure. We mapped it in detail and it looks something like this. So there's a fault scarp here and it dives down under the ground, and in fact it's buried by young sediments. But what we see in this area is a clear example of the gouge of the Alpine Fault. It's quite low angle here, and this low angle faulting that we see at Gaunt Creek is very consistent with a north striking segment of the Alpine Fault. In fact, it's quite zigzagged in this area. Why is that important? Well, recently we've also been using the LiDAR to map out the Alpine Fault in detail along a zone which includes the whole of the west coast region between northern Buller and southern Westland. This has become extremely important for the town of Franz Josef, and this is a really good example of how we can think about fault traces and fault awareness zones. So here we've been using the LiDAR, which is this strip here of about 1.5 kilometres wide along the fault, to map out fault traces and to show in detail where the fault runs through the town of Franz Josef and off into the distance. This is coming up in a district plan hearing starting from Monday in Franz Josef, and it's interesting to see how this will affect the town planning and the businesses and homes that live within this fault avoidance zone. One example of really proactive behaviour is that the Dock National Park people have decided to move on from this area and find a new site where they can set up their national park headquarters. So as well as mapping the fault out and looking at evidence for past earthquakes that we can date, we're also interested in how much slip there is on the fault. So if you're sitting in Franz Josef and the fault line is running through your town, how much is that fault going to move? Well, evidence from looking at things like displaced channels. Here's a channel. This is at the Toaroa River near Hokitika. Here's a channel. It's coming up to the fault here on this topographic map, and it steps to the right as you cross this fault line here. This is a trace of the Alpine Fault. There's a second trace here. This channel comes up. It steps about 7 metres to the right, and it steps about another 1 to 2 metres across the second trace. There's also a vertical component of motion which we can see because our eye picks out the actual line in the landscape. So there's actually 1 to 2 metres of vertical movement across the Alpine Fault as well. So in the next Alpine Fault earthquake, as we've seen from up and down the west coast, here's a diagram, here's Tairua River, is that there will be about 7 to 8 metres of horizontal movement in the next Alpine Fault earthquake and about 1 to 2 metres of vertical movement. This deformation is permanent. Once it happens, it stays there. It doesn't wobble back to where it was before. So the ground will leave a permanent record of that deformation. So another aspect, another spin-off of the work that Ursula's been doing in South Westland is that we've been able to publish a brand new conditional probability for the Alpine Fault moving in the next 50 years. Now, of course, this loaded gun was stolen from a Wellington Fault talk. For the Wellington Fault, there's actually only 1 bullet in the chamber. For the Alpine Fault, it's 3. So there's a 30% chance in the next 50 years of a large to great earthquake on the Alpine Fault. What's that going to look like? Well, there's going to be intense shaking up and down the fault here with decreasing amounts of strong shaking, but felt all over the South Island. And Tom's going to talk about this in much greater detail in the next segment of the talk. And so, is this relevant to Christchurch? Well, I'd say yes, it is. We have to think about what are the levels of ground motion going to be from an Alpine Fault earthquake. And some of the work that's been done by GNS and Mark at the back there and Monica sitting down here has been to look at the geological record of liquefaction in the past. So this site is near Lincoln, and we've been digging trenches there. It's nothing special about a trench, it's just a hole in the ground. But we've been looking at sites where there's evidence of relatively minor liquefaction compared to what you've seen around the city. But we want to know, what does that look like in the geological record? Well, we can see the sand volcanoes, we can see dikes that are related to that liquefaction, and in the sedimentary package we can only see minor evidence for small amounts of liquefaction happening only about once in the last 1,000 years. So there's a big contrast, this is just for this site, there's a big contrast between what's happened in 2010-11 and what we see in the geological record as shown by these sediments. The last subject I'll touch on is we've started to realise that we're telling people about preparedness for the next Alpine Fault earthquake, but as scientists we also have to think about how are we going to be prepared for it and what is our response going to look like. So rupture of the Alpine Fault in a magnitude 8 earthquake will be a natural disaster. There will be huge scientific interest in this event, both nationally and internationally. We'll be flooded with scientists coming from overseas who want to see this event, both in terms of the fault rupture, the sediment dynamics, etc., etc. At the same time, people on the west coast will be living in the middle of a civil defence emergency disaster, as you've lived through yourselves. So our scientific response needs to be coordinated, organised, informative and respectful, knowing full well that the services and the infrastructure on the west coast will be highly stressed at this time. So the take-home message from my talk is that improved on-fault trenching and slip data from up and down the west coast supports the off-fault records that Jamie and Ursula have talked about. Slip in the next earthquake will be quite large, on the order of 7 to 8 metres horizontally and 1 to 2 metres vertically. And the event is inevitable, so all of us actually need to plan for that event. Thank you.
Okay, so I'm going to sort of take a step slightly away from what Jamie and Ursula and Rob have been taking, and instead of looking at past earthquakes, I'm going to start to talk about what this might actually look like for the next event. Particularly in terms of shaking and in landsliding, and then what that might actually mean for us in Christchurch. I think we've sort of got the view now that it's going to be quite bad if you're in the Alps or over on the coast, but what does this mean for us in Christchurch? Yeah, so I'm going to focus on landsliding, as I said. So this is more really of a summary of what Jamie was saying beforehand, but it's something we all know now in Christchurch quite well. Earthquakes are not just the ground shaking and the strong shaking that we feel. We also have the liquefaction, the rockfall, the landsliding, and a whole ream of other effects. And so this is just some examples of how we know that this also happens in Alpine Fault events. So this is the lake cores that Jamie was talking about, and showing you the turbidites in each of the lakes, followed by the post-earthquake sediment flux. And then this is also a map of all of the known really large landslides we've got. So some of the biggest landslides we find in the country, this is the map of where those occur. And we can see that they cluster very close to the Alpine Fault, and then into Fiordland here, where the fault trends offshore and the Persica Trench starts to come in. So we start to get this idea that the shaking is going to be very strong from this quake, but it's also going to have a widespread landscape effect. And so what I'm going to talk to you about is what that might look like for us, and what that might mean in terms of some of our critical infrastructure. So this is a shake map, again similar to what Jamie and Rob showed earlier. And so you can see this is assuming a magnitude 8 full-length rupture. We can see we're getting very high intense shaking right along the length of the fault, and the entire south line is going to be feeling this fault. So to give you a sort of scale, MM6, this is this darker colour around here, that's where we start to see slight damage occurring, things like chimneys cracking, weaker buildings get cracking in their foundations, right up to our MM8s and 9s along the fault rupture, where some of our weaker buildings might start to actually collapse or be severely damaged. To put that in perspective for us, all of us that lived through the Christchurch quake, in exactly the same colours and exactly the same scale, this is the Darfield quake, the extent of shaking, and this is the Christchurch quake and the scale of that. So you can see, for us, this was a huge event. It was felt across much of the city. This is on a whole other scale. We felt across the whole island, and potentially even the nation, up into the North Island. So I tried to map that forward and see what that might mean in terms of landsliding and landslide hazard. I've specifically not detailed the method because it's exceedingly boring, even for me, and I don't want to subject you guys to that in your lunch break. But basically, it's based off of observations of previous events, some of which Jamie was showing in Wenchuan and Chi Chi. So this is that landslide hazard map that we're able to produce. It's based on a relative scale from 0 up to 1, where 0 means we would generally expect there to not be any landsliding, and 1 being that we would expect there to be some form of landslide. Not unexpectedly, as you can see, it focuses right onto the fault rupture, right across the length of the Alps, and we're even getting into quite high, above 0.5, so where we're starting to expect landsliding, spreading right out and covering almost the entire Central Alps. For us over here in Christchurch, we don't see those high values, particularly up in the Port Hills and in Lyttelton Harbour, which ties in quite well with some recent stuff that Mark just over there has been finding, and that these big regional quakes might not do the same things to the Port Hills that we saw in the Canterbury quakes, but do quite a bit of damage up in the Alps. So if we're to take out some of the highest hazards of that area and start to look at what that might look like, what area that might cover. So this is taking out just the very highest landslide values that we see. And you can see, again, these cover the entire fault rupture. These stretch back into the Alps by about 5 to 10k, particularly, perhaps even more so, up here in the Arthur's Pass region. And what that might mean for our landscape is that we might go from these beautiful green, heavily vegetated Southern Alps that we're at now, we might end up looking something far more like this, which is a picture from Wenchuan. Wenchuan's quite a good example. The earthquake was very similar to what we what we think we're going to experience. Magnitude 7.9, 400-kilometre rupture, heavy, intense shaking. Very originally vegetated mountains, which subsequently ended up looking like this. And this is what we might expect to see through this entire area here. So landsliding is going to be a major problem after this quake, as well as ground shaking. But what might this mean for our critical infrastructures, particularly in terms of our road and our power, which connect us around the South Island? So this is our state highway network. I'm sure we've all driven along most of these roads over onto the coast. And this is really important for some of our major industries. So in terms of our getting general access, if you want to go and visit Greymouth or Hokitika, you need state highways. Tourism, constantly people driving on our roads all over through the passes, but it's also good for, it's also really important for our goods transport, particularly in terms of getting dairy products over from the dairy fields in North Canterbury or over on the west coast, mining up in the in these ranges here in Greymouth. It's a really important network for us. but it actually has very little redundancy. We've only got the Lewis Pass, Arthur's Pass, and Haas Pass that connect us to the coast. We've only got really 2 roads that run north and south, one along the west coast and one along the east coast. So if we start to look at how exposed to landsliding they might be, given what we're expecting, this is the map that we can produce. And again, so this is on a scale, 0 to 1 relative scale, where 0 and our greens, the deeper the green, the less likely we are to anticipate landsliding. So quite obviously, if you drive down to Timaru, really boring drive, no topography, so we're not expecting any landslides there, obviously. But once you start coming in through Arthur's Pass, then we start to see much higher, much deeper red colours, where we really start to expect landslides, and where in fact it's quite possible that we have massive blockages. What this exposure map is showing us is that each of the passes, so Haas Pass, Arthur's Pass and Lewis Pass, are all heavily exposed to landsliding. It would be extremely unlikely that these would not witness some sort of landsliding, and particularly State Highway 6 south of Hokitika. There's very little of that which isn't considered to be exposed, and one of the highest sections here is between Franz Josef and Fox Glacier, which if you've ever driven is scary enough without an earthquake, let alone after an earthquake. To get away from sort of maps and colours, this is sort of a visualisation of what that might actually look like. So in our big deep reds in between Franz and Fox and up in Arthur's Pass, these are the kind of landslides that we could be seeing. These are the kind of impacts to our highways that we could be seeing. When we get into sort of our oranges and still up very high, we still expect to see big landslides. So somewhere in Lewis Pass, not as bad, but still not something you want to be driving underneath or trying to drive through. And then up into our yellows and sort of our higher greens, we might see something more like what we saw up on the Summit Road, with broken up rock falls, still some potential access, nowhere near as bad as these, but still on a high level. So that's going to pose quite a big problem for us post-earthquake, particularly long-term in restoring these lifelines. But what I want to do is I just want to zoom into this little area here in the Grey Valley, because this is what we consider to be one of the most critical sections of our network. So this is a zoom of that view, and what you're looking for is, this is Arthur's Pass coming through to Greymouth and Hokitika, and then this is the Lewis Pass coming through here, and then this is in the Buller Gorge. What we're seeing here through Lewis Pass, we're getting those high oranges and not quite up to the reds. In Arthur's Pass, we're seeing the great big reds. Between Inangahua, Reefton and Greymouth, which is misplaced for some reason, but Greymouth, we're not seeing those very deep colours. We're not expecting this section of road to be blocked by landslides. And so it's absolutely vital in this area that the road is able to cope with the shaking that it's exposed to. The bridges are able to sustain any liquefaction they might be exposed to as well. Because if we push that forward, in the Arthur's Pass, to get to the coast, we're going to be contending with this. To get through Springs Junction and the Lewis Pass, we're going to be contending with this. We're coming in from the north through Nelson, we're only going to be contending with rockfalls. And if you have a choice of which one to clear up to gain access, it's pretty obvious to see you're going to go through that one. So if you've just spent all this time clearing up your rockfalls through the Buller Gorge, the last thing you want to do is get here and find that every single bridge is out and you can't get through. So maintaining the bridges in this area is absolutely critical, and actually can maintain access to around about 30,000 people who live on the coast in Greymouth, Dobson, Reefton, and as far down as Hokitika. So that's a really critical section going forward. If we start to move away from our roads and start to look at our HEP, our hydroelectric power and our transmission network, that's equally interesting. So again, like our roads, it doesn't have an awful lot of redundancy. On the east coast, there's a lot of redundancy. We're pretty okay. But once we start going east to west, there's only one line, goes through from sort of Lake Coleridge through Arthur's Pass, and then in through Buller. That provides all the power from the hydro that goes into the west coast. So these areas are already prone to landsliding. I'm sure you can expect what it's going to look like, particularly through Arthur's Pass. So again, this is the exposure map that we might see for that. Again, over down here on the east coast, not much topography, not an awful lot of shaking. We wouldn't expect to see huge landslides affecting these power lines. But again, once we start running through Arthur's Pass, particularly again south of Hokitika, we're starting to see very high exposures from landsliding. And again, with these are the areas we'd start to see losses to the hydroelectric power lines. In terms of what this network is made up of, primarily on the east coast and just in the earlier bit of Arthur's Pass there, it's comprised of big steel towers that we see. Once we get over onto the west coast, that's composed primarily of small poles, wooden poles. So again, to give you an idea of what that means, what these colours mean, they get away from colour and just to actually what it might look like. It's actually very difficult to find images of landslides that have hit these structures, generally because they're either buried underneath it or sort of don't exist anymore. But these are the kind of damages we'd be expecting to see. So where we have steel towers in Arthur's Pass that are exposed, completely knocked over, perhaps even broken into pieces. And over on the west coast, we've got poles. If they're built up on the landslide or underneath the landslide, we might see entire sections which are completely bent over. That's going to take a lot of time to fix. Repairing one of these is on the order of 2 days or more. Repairing each pole could take 6 hours, maybe a bit more, but if you have substantially more of them because they're less spaced out. So this starts to become a big problem for getting power into the West Coast region. So what might this look like for us? So we can start to see that this event, when it happens in the near future, it's going to be very different to what we have experienced in Canterbury. So in Canterbury earthquake sequence, we experienced substantial damage and losses. In Christchurch, we wouldn't expect that from an Alpine Fault event. The shaking will be strong, and we certainly feel it, and we might even see some slight damage, but we wouldn't expect to see the major losses that we saw in the Canterbury earthquake sequence. But our regional economy, which performed so well after the Canterbury earthquake sequences, that may be quite exposed to an event like this, due to the fact that we have such wide infrastructure losses in the Alps. Lewis Pass, which is going to be absolutely critical for us gaining access east to west, may take up to 6 weeks to reopen in that region. Arthur's Pass may even be inaccessible for up to 6 months. And what this means in terms of getting dairy and mining goods from the coast where they're produced through to us here in Christchurch, where we distribute them and move them around. What this means in terms of tourism. Christchurch is a great gateway tourism entry. People come here, stay here for a few days, and then jet off to other parts of the South Island. If we have lost our passes over to where they want to go to in 6 months, what does that mean in terms of our tourism? So we start to see our regional economy is what is going to be exposed in this event. Restoring our power lines. If we lose several steel towers up through Arthur's Pass, we're talking about weeks possibly to repair. And once we start to look at some of the poles that we might lose over the coast, we're talking thousands of man hours. And this is once we've gained access. If we go back at that, Lewis Pass is going to take up to 6 weeks. So it's restoring these lifelines is going to be the major impetus post-earthquake. And so if we're thinking pre-earthquake, it's these things that we need to be focusing on, particularly from a Christchurch point of view. We're focusing on these key industries, which are all need reliable access and power to function. So I just want to finish up by kind of having some take-home messages or some conclusions on all of our talks and mine, just to really summarise it for you. So what we're starting to see and what we're starting to realise is an Alpine Fault is extremely likely in the next 50 years, may even be absolutely certain in the next 100. It's expected to be around about magnitude 8, so that's an order of magnitude larger than the Darfield earthquake. And it will be very different to what we have experienced here in the Canterbury earthquake sequence. Christchurch is unlikely to experience those massive losses and those big building damages. But widespread associated hazards, landsliding and that up in the Alps will present a long-term issue, and it has the promise to put our regional economy at quite high exposure. And so our pre-event focus, when we're talking about this event from our point of view over here in Christchurch, is we need to be focusing on planning for widespread infrastructure losses and for how our economy can deal with those in the long term. Particularly, and whether that involves installing mitigation to perhaps reduce those losses, maybe even in fact planning for fast and effective response to clear those up in even quicker times, reducing our dependency on these infrastructure links. There are a number of different things we can do, and that's where we need to work forward to now that we have all this information that these guys have been able to produce. This is what we over in Christchurch need to really be thinking about. So any questions for all of us, I guess?